Hi, I'm Martin.
Hi everyone, I'm Nargis, and we are going to talk to you about our work, lightweight and modular resource leak verification. Resource leak occurs when some finite resource managed by programmers is not released explicitly, when it's not needed anymore. The resource might be a file descriptor, database connections, or a socket like the example in this slide, or any other finite resources in a system. We know that sockets are released by calling close on them. So if a programmer forgets to call close, like here, then we have a resource leak. Leaking finite resources in a system might cause resource starvation, slowdowns, system crashes, or denial of service attacks. You see, this is a serious problem, such that Microsoft engineers consider this as one of the most significant development challenges. So we would like to have a tool to prevent it. But the key challenge in detecting resource leaks is handling aliasing, since there might be multiple references to a resource object, and close can be called on any of them. But how have previous approaches addressed this challenge? One approach is finding resource leaks heuristically, that mostly ignores aliases, and it leads to both unsoundness and imprecision. The other one is ownership type systems, like Rust. These tools handle this problem by imposing control over all aliasing. So every value associated with a resource must have a unique pointer, which is restrictive and is too hard to apply to existing code, because it requires a significant rewrite that is often infeasible. The other approach is whole program analysis that tracks all aliasing, which is too slow for large-scale Java programs because tracking all aliasing is expensive. So all of these previous techniques are either unsound, imprecise, inapplicable, or slow. In this paper, we looked at this challenge in a different way. We've showed that detecting resource leaks is an accumulation problem, which is a special case of type state problems in which FSM contains no loops. And the key property of accumulation analysis is that it's sound with no alias analysis. But how leak detection can be an accumulation problem? We know that the resource is released by calling close on that. And if close is not called on the object before its reference becomes unreachable, then we have a resource leak. So if we assume that being unreachable or going out of scope is an operation, then the FSM looks like this. As you can see, we don't have any loop except self loop. So we can say that checking resource leaks is an accumulation problem. And a recent study showed that accumulation analysis doesn't require alias analysis for soundness. And because of that, it can be implemented modularly. So without having any concern about aliasing, leak detection boils down to 3 steps. First, computing what methods must be called on each variable, like close on sockets. Then computing what methods are called on the variable at each program point. And at the end, issuing an error if there is a mismatch between the result of these 2 computations before the variable goes out of scope. Consider this simple example. After this assignment, our analysis computes that close has to be called on S, and it starts tracking S on all paths. Then it computes a set of methods that are called on S at each program point. In this slide, the result of this computation is shown on 2 program points, where the reference of the resource object becomes unreachable. And it reports an error here because close is not called on S, and S is going to be unreachable because of this assignment. However, it can verify that S is properly released here. This analysis is sound, but imprecise without having alias analysis. It can't even handle this simple example, in which T and S are must aliases, and close is called on T. So Martin is going to explain to you how we improve the precision in our tool.
Thanks, Nargis. One of the key benefits of using an accumulation analysis like the one that Nargis described is that although it's sound without any aliasing reasoning, you can always do local and cheap alias reasoning to improve its precision. And so that's how we made our tool's precision reasonable. We did this with a series of local alias analyses, one of which computes local must aliases that handles the case with TNS, the one that Nargis described. And I want to give you a flavor of some of the others just so that you have a general idea of what kind of things we were doing. So first, I want to talk about our lightweight ownership system. This is useful in situations like the one on the left side of your screen, where there's some method, close socket, that's going to take responsibility for closing some socket like my sock in this example. However, naively, our analysis doesn't know anything about the implementation of close socket. So if there's an obligation to close my sock before close socket is called, that obligation will still be there afterwards. In order for the analysis to figure out what's going on here, it needs some information about closed socket. It could get that in one of two ways. First, it could do an interprocedural analysis and no longer be modular, but that sort of defeats the point because we want a modular analysis. That's one of the reasons we're doing accumulation in the first place. Or it could have a specification, and a specification is the approach that we took. So the programmer would modify the definition of closed socket here to include this orange at owning annotation. So this at owning annotation is the specification. And it says that calling closed socket moves the obligation over into closed socket. So any obligation that was present on the parameter then becomes the responsibility of the implementation of closed socket. This is a really nice approach because obligations are neither created nor destroyed by it. So it's sound, but it doesn't restrict the privileges of other aliases that may or may not exist for my sock. And that's in contrast to obligation or ownership type systems like you might find in a language like Rust. Another kind of local alias reasoning that we do is resource aliasing. So if you have code like this, where you have a socket and this stream that wraps around the socket, you might reasonably ask the question, which of these ought to be closed? Is it both, or is it one or the other? And the answer actually is that it doesn't matter. And that's because closing either socket or stream is equivalent. If you call it on stream, then socket will also get closed, right? The underlying resource is the same. And previous approaches had handled this kind of problem by just having a predefined list of classes that had this property. Our approach is nice because with the cost of a few annotations from the programmer, they can write and verify their own classes that have this property instead of just relying on a predefined list. All right, so that was some idea of the alias reasoning that we do. Finally, I want to talk about how we evaluated the tool that we actually built, which was for the Java programming language. One of the things we did was we did a series of case studies, including the programs that are listed there. We found 49 real resource leaks in these programs. The precision of the approach in these examples was about 29%. I'll come back to that later and how that compares to other extant approaches. And we had to write about one annotation for every 1,500 lines of non-comment, non-blank code. And these are annotations like the at owning annotation that I mentioned earlier. We also did a comparison study between our approach and two other state-of-the-art approaches. Right? So our approach is RLC, that's the name of the tool. Then we have the bug finder that's built into the Eclipse IDE. And we also have Grapple, which is a whole program graph reachability analysis that was published at ESEC 2019 and is notable for using a whole program alias analysis. In recall, you can see that RLC is the only one that is sound, so it finds all the bugs, but Eclipse and Grapple miss the vast majority of real leaks. On precision, I mentioned RLC's precision is about 29%. As you can see here, that's pretty comparable to the other approaches as well. Finally, on time, Grapple's whole program alias analysis takes about 37 hours on these benchmarks. It's a long time, and these are reasonably sized programs, normal programs. If we zoom in here, we can see the difference between RLC and Eclipse. So on a 1 hour scale, you can see here that RLC is taking about 25 minutes, whereas Eclipse takes under a minute. Right? So the cheap data flow analysis that Eclipse does is much faster, but RLC gives you this recall increase. So finally, I want to just go over our contributions. So we've shown that you can do lightweight and modular resource leak verification as opposed to bug finding by using an accumulation analysis, which is a special case of type state. Right? And you can make that analysis competitive on precision by doing local alias reasoning. You don't need to do a whole program alias analysis. And we did an extensive evaluation of the approach, and then we built an open source implementation. You can find that at checkerframework.org. It's under the name the Resource Leak Checker. That's it. Thanks for listening, and we're happy to take any questions that you might have.